Section 2.1, the tangent and velocity problems. Now, this section is going to lay a lot of the groundwork for a lot of our discussions going forward. The question is like, well, what the heck is calculus all about? I mean, what's the big deal with calculus? Well, one of the things that calculus allows us to do is come up with a way to describe the behavior of a function. In other words, if I have a function that is used to model a particular situation, I'm interested in what the behavior of that function is or how the values of that function change over time. So do the values of the function get larger? Do they get smaller? Are they increasing or decreasing? Are they increasing rapidly or decreasing at a slower rate? That kind of thing. So if you keep this in mind as we discuss, ultimately it's going to be all about what we call derivatives. And if you've done any work with calculus, that rings a bell. Obviously, it's going to be one of our big topics. But it's all about rate of change. All right, keep that in mind. What's the rate of change? How does the function value change over time? All right, increasing, decreasing, rapidly, slowly, that kind of idea. Now, if we start with the most basic type of function, like a linear function, right? Linear function, the graph is a line, right? And you want to talk about the rate of change of a line. Well, we have a formula for that. That's what we call the slope, right? The slope of a line, its rate of change, its rise over run, right? It's change in y over change in x, if you wish. But that's a basic function. We can take any 2 points on the line and we can calculate the slope of the line. We have a slope formula for doing that. Well, what happens if the function is not linear, right? I mean, real world, you got to consider that most functions are not going to be nice straight lines. They're not going to be linear functions. So how do we describe, or how can we come up with a way to describe the rate of change of that function if it's not linear, right? And so that's essentially what the derivative ultimately is all about. And so we need to come up with a way of understanding what the heck a derivative does, not just being able to find it, which is what we're going to spend a lot of time doing in chapter 3, but what exactly is it that you're finding, right? So we don't want to lose that concept. And then we're going to put that into use in the context of real world type applications, okay? All right, so since the linear function, a line, where we have a way to calculate the slope of a line, if I'm going to try to calculate the rate of change or slope of a nonlinear function, then let's make use of what we know about lines. And so we're going to start with that tangent line that we mentioned back in that review section. And so here's a working definition of what we said the tangent line was. We said that a line tangent to a curve touches the curve at exactly one point and has the same direction as the curve at the point of contact. Right, so this is where we said, if you look at the diagram that I have, the curve is y equals x squared. And I said if you take your pencil and you put it along that tangent line as I have drawn, touching that point, that curve at the point 1, 1, and then you move your pencil to where it only touches the curve at one point, your pencil is forming a tan line, right? And at that point of contact, the slope of that tan line is the slope of the curve. It's the rate of change, or the rate at which that curve is changing, or the values of the function are changing at that specific point. Right? So if I can calculate the slope of that tan line, then I can give you the slope of the curve. Right, now, we start off here first talking about the equation of the tan line, right? So I can come up with the equation of a line, and there's different ways to do that I'll remind you of. But if I want the equation of the tan line, or again the general idea, I just want to describe what the rate of change is of that function, we need to know its slope. Right? But there's a problem. I only know one point. And if you want to find the slope of a line, remember you have to have 2 points on the line in order to use the slope formula. Right? It's that change in y over change in x idea. So I can't just use directly the tangent line to find the slope of our curve, because of the fact that there's only one known point. And I need 2 to find the slope of a line. So what we do then is use instead what we call the secant line. Now notice these are very familiar terms to us from trigonometry, right? Tangent line, secant, those are trig terms. Well, that's not a coincidence. There's a reason for that. Right? Now it's not necessary for our purposes here, right? But it's not just randomly chosen names. There's a reason why it's called the tangent line and the secant line, and it has to do exactly with the trig idea, but not part of our discussion. So we're going to use a secant line, and a secant line, by definition, is a line that intersects a curve at two or more points. All right. So if you look at the graph that I draw, I tried to draw it a little bit nicer than what I had there originally. So here's our curve, y equals x squared, or f of x equals x squared, if you wish. And then I've got this point 1, 1. And at that point 1, 1, I drew the tangent line. That's the red line. All right, so similar to the diagram that we have above. So there's our tangent line at that point. And then I chose a second point. Now, I called that point Q. I just randomly chose, or you could choose any point to be point Q, the second point. What are the coordinates of that point? Well, it's whatever the x coordinate is that we choose it to be. And since our function is y equals x squared, then the y coordinate is x squared. Right? So generically, this point Q would have coordinates x squared. Right? So you could pick any x value, plug it into the function, and get the y value. And then you have the coordinates of that point. So we're choosing a second point, whatever it may be. And then we have the secant line. That's the blue line. All right, so drawing through those 2 points, hitting the curve at 2 points. All right, so tangent line, secant line, difference between the two. Now, we can use the slope of the secant line, call that m sub pq, right, slope of the secant line, passing through the points pq, to approximate the slope of the tangent line, which we're going to call m. All right, so we'll say that m sub pq equals m, or that should be approximately equal to m. Now, in order to do that, right, so you look at the two lines. Now, I have these drawn to where points P and Q are not very close to each other. But think about this. If you take that point Q, let me change this color, how about yellow? If I take this point Q and I move it along the line, closer and closer to that point P, and you draw in those secant lines that are passing through point Q, as that point Q moves down this curve and gets closer and closer to P, then that secant line starts to look more and more like the tan line, right? It gets closer and closer to resembling the tan line. So we can calculate the slope of the secant line using points for Q that are closer and closer to point P, which is at 1, 1. And then if you look at the slopes of those secant lines, and say, okay, well, what are the slopes of those secant lines doing as Q gets closer to P? Then that gives me an idea of what the slope of the tangent line at that point P would be. That's the basic idea. Now, and if you want some prettier pictures, you can always look in the textbook, right, or your e-text. Y'all have textbooks, so y'all can use your textbook. And if you want nice, prettier pictures than what I have drawn here, then you can look in your textbook and see those a lot more clearly. So now, here's the idea. All right, so Q is getting closer and closer to P. And notice the notation. Half the battle. I always say this when I'm doing any math class. Calculus is certainly no different, probably even more so. Half the battle in understanding the concepts, understanding the topic, is understanding the language. And in calculus, you can throw in understanding the notations, right? So you have to understand the terminology, you have to understand the language, you have to understand the notations. That's half the battle, or maybe 2/3 of the battle in terms of calculus, all right? So when we talk about a tangent line, you have to know what that is. You talk about a secant line, you have to know what that is. And then you have these notations, right? So we say as Q gets closer to P, or say something like this. It's not what I wanted. As Q gets closer to P. Or we say as Q approaches P, is the other way we say that. Then the slope of our secant line, which we called m sub pq, is getting closer to the slope of the tangent line, which we're calling m. All right? So then the slope of the tan line m, we say, is the limit of the slopes of the secant lines as Q approaches P. All right? So the slope of the tan line is the limit of the slope of the secant lines as Q approaches P. And that's where that little limit notation comes into play that I kind of mentioned in that previous section. So we say that the limit as Q approaches P of M sub PQ, which is the slope of our secant line, equals M, the slope of our tangent line. Notation and terminology. So we're going to choose points for point Q, whose coordinates are x squared, that are close to our point P, coordinates 1, 1. Right? And like I said, in my general little diagram, I mean, I would say that point Q was not very close to point P in the big scheme of things. We want point Q to be really close to point P. And then we're going to pick values that are, for x, that are getting closer and closer and closer to 1. Because I want to get closer and closer to that point with our point Q. Now, we have our slope formula, right? Because our secant line, we have 2 points on that line. We have point P and point Q. So we have our slope formula, slope of our secant line, M sub PQ. There's our slope formula. But that guy, rise over run, change in y over change in x, y2 minus y1 over x2 minus x1. So if I maybe let point P be our first point, right? So we could say here's x sub 1, y sub 1. And then point Q could be our second point. So here's x sub 2, y sub 2. And then we can use our slope formula and say y2 minus y1 over x2 minus x1. So I've got x squared minus 1 over x minus 1. And there is a formula that we can use to calculate the slope of our secant line for any given value of x that we choose. Right? Now again, we want to choose values of x that are getting closer and closer to 1 because our point in question is the point 1, 1, whose x coordinate is 1. Now you'll also hear me say this a lot. When you are evaluating a limit and you're looking at the behavior of your function as x approaches a particular value, you want to look at what happens as you approach that value from both the left and the right. You know, so let me draw this real quick for reference. You know, here's the side of our point. So we have our point 1, 1, and here's x equals 1, right? And so we had that point Q up here, and then we're moving that point Q closer and closer to this point. So I want to choose values of x that are getting closer to 1 from this side and also from this side, because you want to observe what's happening from both directions. And there's a reason for that, as will become plainly obvious as we move through this stuff. All right, so we never just consider one side unless we're only focused on one side. All right, so in general, we want to look at what's happening from the left and from the right. So I have these 2 tables, and these again just reproduced from the textbook, but all these tables is using our formula that we have up here. All right, that's our slope formula for calculating the slope of our secant line for the given x value that we choose for point Q. And so I have the first table, which are values of x that are approaching 1, notice from the right side. So 2, 1.5, 1.1, 1.01, 1.001. These are typically the types of values that we're looking at. You know, when we say that we want to get close to 1, we want to get really close. You know, 2 is not very close to 1 when you're trying to calculate the slope of a tan line. You want to be really close to 1. So you'll typically choose values like 1.1, 1.01, 1.001. That's coming from the right side. Notice the chart on the right. Those are x values that are approaching 1 from the left. Right? Those are values that are smaller than 1. And again, this is typically what you would be looking at. So I want to be really close to 1, 0.9, 0.99, 0.999. So those are typical choices, you know. So when we say pick values that are close to our number, we mean really close. And then all we're doing is we're taking those x values and we're plugging them into our slope formula. So that's where those M sub PQ values come from. That's where these y values come from. So if I plug in 2, I get 3. Plug in 1.2, I get 2.5, etc., etc., etc. And then what we're interested in is making an observation about what happens to the slopes of those secant lines. What happens to M sub PQ as x gets closer and closer to 1. And in both cases, we can see that M sub PQ is getting closer and closer to 2. Right? 2.1, 2.01, 2.001 on this side, but they're getting closer and closer to 2. Here, 1.9, 1.99, 1.999, but again, getting closer and closer to 2. So here's an observation, and this is exactly that. It's an observation about the behavior of the slopes of the secant lines as the x values, as those x coordinates of point Q are getting closer and closer to 1. So since m sub pq, since the slope of the secant line gets closer and closer to 2, then we can say the limit as q approaches p of m sub pq, right, which now could also be said is the limit as x approaches 1 of our function x squared minus 1 over x minus 1, right? That was our slope formula, is equal to 2. So there's the notation. And we're using that, or we're saying that that would be m, the slope of our tan line, right? Now again, this is an observation based upon the information that we have in those charts, in those tables. All right, so it's based upon our observation about the secant line slope as x approaches 1. Now, we started off originally, we said, what's the equation of the tan line? Well, bulk of the work is going to be in finding the slope, right? Because if I want to write the equation of a line, I have to know its slope. Once I have the slope, then I can write the equation, right? So with m equal 2, we're approaching the point 1, 1, so there's our point in question on the line. We can use the point slope form of the equation. Now, there's a couple of different ways that you can find equations of lines. Some of you, if you remember, may prefer to find the y-intercept and use that form. I like using this point slope form. Remember, that's that. There. Do that a few times as we go through. But that's this guy. Remember this y minus y1 equals m times x minus x1? That's the point slope form of a linear equation. And if I know the slope of the line, which we now know, and I know a point on the line, any point, then I can plug that into that equation, solve it for y, and now I've got the slope-intercept form of the equation of the tan line. Right. Now, again, I know there's different ways that you can do it. If you prefer to do it the other way, you remember how to do it using slope, the y-intercept, that's fine. But I recommend doing it this way because that's the way I'm going to do it. And there's reasons for that. There's other applications of this thing that, if you're familiar with using this method, makes those concepts just a little bit easier. So I always find the equation of a line using the point slope form. So we plug in our point, which is 1, 1. We plug in our slope, which we found to be 2. And then we're just solving that for y, right? So when I distributed the 2 and added 1, I get y equals 2x minus 1, which is the equation of the tan line. Now, like I said, at this point, my main concern, my main interest is finding that slope, right? So sometimes you'll be asked to find the equation of the tan line, great, but it's typically going to be all about finding the slope of the tan line. It's all about the rate of change, right? How the function is changing. Now, that's a situation where we actually had a function, right? We came up with a formula that we could use to calculate the slope of the tan line at a specific point using observations about the slope of the secant line. All right, and we were able to choose values for x that got really, 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 really close to the point of interest. Here's another situation, though. And this is coming from the homework section. This is on page 82, number 2 out of the text, where here I don't have an equation. All I have is data, and I summarize the problem here. So there's a table of values for t and h, where h is the number of heartbeats after t minutes. So we have heartbeats per minute. If you look at that in terms of your x and y, your input and output. So after a certain number of minutes, t, we can count a certain number of heartbeats, h. So you could think of those as your x and your y. And if we look at the ratio, heartbeats to number of minutes, right? Change in number of heartbeats over change in minutes, that's our heart rate. Okay. So we can calculate the heart rate as the ratio of heartbeats per minute. And if we're interested in the rate of change, right? What is the heart rate Well, that's going to be given by the slope of our tan line. So what is your heart rate at a specific point in time? So what is my heart rate in this case? Our question is, let's estimate the heart rate after 42 minutes, right? Or at 42 minutes, what is the heart rate? Heartbeats per minute. Now, be careful in the language here. There's two different heart rates that can be calculated. I can calculate the heart rate at 42 minutes. We call that the instantaneous heart rate, right, at that specific point in time. Or I could calculate an average heart rate, say over an interval of time. So what if I said, well, what was the average heart rate after 42 minutes? Well, I could look at the total number of heartbeats, 2,948 heartbeats in 42 minutes, and I can give you the average heart rate by dividing 2948 divided by 42, and I can give you the average heart rate per minute. But that's not what we're asked for here, right? So we want to be clear as far as which one we're talking about. And in terms of rate of change, we're interested in that instantaneous rate of change. What's happening at that specific moment in time, not an average over an interval. But it's the same issue as before. And even more so here, because I don't even have a function to work with. All I have is data. I'm going to look at the average heart rate over time intervals that are getting closer and closer to that 42-minute period. In other words, if we look at the average heart rate over the interval from t equals 36 to t equals 42, right? Change in number of heartbeats per change in time. So if I take the difference in heartbeats divided by the difference in time, that would give me the heart rate over that time interval from 36 to 42 minutes. But that's just an average over that time interval. And then we can look at the average heart rate over the time interval from, say, 38 to 42 minutes. So I can take the difference in heartbeats between those two times divided by the change in time, which would be 4 minutes. And again, I can give you an average heart rate over that time interval from 38 to 42 minutes. Get the idea? And I can do the same over the interval from 40 to 42. Okay? So if I take the average heart rate over this time interval, so what I'm doing is I'm calculating the average heart rate over these smaller and smaller intervals. That's exactly what we did with the secant line in that previous problem. Remember, we were taking x values that were getting closer and closer and closer to the point in question. And in this case, the point in question is 42 minutes. And we want to know what's happening right there at that point in time in terms of the heart rate. So it's the same idea, just a little different application of it, in that we're looking at smaller and smaller time intervals. I'm choosing, look at these as our x values. I'm choosing x values that are getting closer and closer to the x value in question. These are our y values. Right? And so we can calculate the slope of the secant line, quote unquote, over those smaller and smaller time intervals that are getting closer and closer to 42 minutes. And then we can use that observation to maybe give us an idea or make an approximation to what the heart rate was at 42 minutes. Right? So that's what these calculations are. Right? So there's part A, B, C, and D in terms of the calculations that were done, but it's all just calculating the average heart rate over these different time periods. So there's the change in number of heartbeats over change in time for each of those time intervals, from 36 to 42 minutes, from 38 to 42 minutes, from 40 to 42, and then we also went 42 to 44. And we have an average of 69.7 beats per minute, 71.75, 71, and 66, but that's where those calculations come from. Right? Now, since we are interested in, our original question was, what was the average heart rate after 42 minutes? Well, unlike that previous example, like we said, we had an actual function and we could get really, really close to x equals 1. The closest I can get to 42 is to say, well, let's look at what happens on this side of 42, from 40 to 42. And let's look at what happens on this side of 42, from 42 to 44. So on the interval from 40 to 42 minutes, we come up with an average heart rate of 71 beats per minute. On the time interval from 42 to 44 minutes, we come up with an average heart rate of 66 beats per minute. So what that tells me then is at 42 minutes, at that specific point in time, well, the heart rate has to be between 66 and 71 beats per minute. Right? But that's really the best that we can do because I can't get any closer to 42 to give me any better information. So I know it has to be between 66 and 71. So what we're going to do in this case then is, okay, I know it has to be between 66 and 71, so let's just average those two. And so at t equals 42 minutes, a heart rate between 71 and 66, just based upon, again, the observation that we made from the calculations. And so then we're using the average of those two just to give us an approximation and say that, okay, I'm going to approximate the heart rate at 42 minutes to be approximately 68.5 beats per minute. Does that mean that's what it is? Maybe it is, maybe it isn't, but it's the best estimate that I can give based upon the data that we have. Right? So it's not an exact science in this case because I can't get any closer to 42. Now, if you notice below that, I went ahead and did the average heart rate. Because remember we said originally if you want the average heart rate over the 42-minute time period, then we would take the number of heartbeats, which was 2948, divide by 42 minutes, and you get approximately 70.19 beats per minute. Notice that's quite a bit different than what we came up with for our instantaneous heart rate at 42 minutes. Right? So those are two different things. And sometimes it may be the same, you know. It may just turn out that at a specific point in time, it's exactly the same as the average. But generally speaking, that's usually not going to be the case. Right? Now, we started this section off with the title Tangents and Velocity. All right, so all that discussion so far has been about the tangent line, or at least the idea of the instantaneous rate of change using the tangent line or slope of a tangent line at a specific point. Well, here it is in the specific context of velocity. We're going to talk a lot about velocity in the context of calculus because that's one of the real applications of this. Motion, particle motion, motion of an object, that kind of thing. A lot of use for this in like physics, those types of areas. So a lot of discussion and a lot of applications dealing with velocity. Right? So velocity is defined as change in distance over some unit of time. Right? It's your rate of change in your position. Right? That's what velocity is, right? So as my position changes, how fast is my position changing? How fast is my location changing? Right? And so again, anytime you're talking about rate of change, well, there's a slope of a tan line. It's the same idea. What's happening? What's the rate of change at a specific point in time? Or we could talk about rate of change over an interval of time like we did in the previous problem with the heartbeats. Right? So it's the same general idea. Now, there's two different types of velocity, right? So just like with the heart rate, we said in the previous problem, we could be talking about an average heart rate over some interval of time or the instantaneous heart rate at a specific point in time. Same thing with velocity, right? So in general, velocity is change in time, or change in distance, over some unit of time. So let's say, for example, 60 miles per hour, right? That's velocity. Now, there's two different velocities that I can describe. That could be describing an average velocity, which would be our change in position over some elapsed time. So let's say, for example, you travel 300 miles in 5 hours, right? Well, 300 miles divided by 5 hours gives me 60 miles per hour. But that would be your average velocity over that trip, right, over that time span. Does that mean I was traveling 60 miles per hour at every point in time along the trip? Of course not. No. I mean, you're speeding up, you're slowing down, your velocity is constantly changing. Maybe you hit a steady velocity for some time interval, but at some point you're going to have to slow down or speed up. So it changes, right? So then we talk about our instantaneous velocity, right? What is the rate at a given time? And again, there's the slope of our tan line. Anytime we're talking about instantaneous rate of change. So that's why, as I said, the section is titled Tan Lines and Velocities, Instantaneous Rate of Change, and the tan line. It's exactly the same thing. All right. So it's all just the language. It's all the basic terminology that's used to describe it. So here, for example, and this will be kind of similar to the previous problem, in that we're looking at the rate of change over a time interval and using that to approximate what's happening at a specific point in time. It's just in this case, we're actually going to have a function to work with. So it's kind of combining the two examples that we've worked previously. All right, so for this one, for example, we have a ball that's dropped from a tower 450 meters tall tower. The distance that the ball has fallen in meters after t seconds is given by that function s of t equals 4.9 t squared. We're asked to find the velocity of the ball after 5 seconds, right? So our velocity at t equals 5, our instantaneous velocity. What is the velocity of that ball at the point where t equals 5 seconds, at that 5-second point in time? So what we're going to do is similar to what we did with the heartbeats. We can look at the limiting values of the average velocity over shorter and shorter time periods starting at 5 seconds. So like we did with the slope of the tan line to that curve y equals x squared at the point 1, 1. And we looked at the slope of the secant lines using x values that were closer and closer to 1. For the heart rate problem, right, we were interested in the heart rate at 42 minutes. So we looked at the average heart rate over time intervals that were smaller and smaller, getting closer and closer to 42 minutes, right? And then we use our observation to approximate the heart rate at 42 minutes. So that's going to be basically the same idea here. We're going to look at smaller and smaller time intervals. Now, since we actually have a function to work with this time, we can get really close, like we did in that first example, because I can calculate values for s of t. I can calculate the distance using really, really small values or intervals of time, right? Because we actually have a function that we can use to calculate them. So similar to that first problem. All right, so but again, what I'm more worried about here is just the language, the terminology, because all these problems are exactly the same. The first example, the second example, and now this one, they are exactly the same in how we're calculating the value ultimately. It's all just different context, different language, okay? And when you work the application, when you work the problems in this section in your homework, that's what you're going to see. They're basically all going to be worked the same way. But the wording, the setup, the language is going to be a little bit different in each case, right? So it's part of the job is to recognize that, hey, that's all just about finding slopes of secant lines and using the slopes of the secant lines to give me the slope of a tan line. That's all revolving around that concept, all right? So in this case, back to our problem, we want to know the velocity at 5 seconds. So we're going to use time periods that are smaller, closer and closer to 5 seconds. So we're starting with, remember we said we could use really, really close values, try that again, that are really, really close to 5. So we have time intervals, say, from 5 to 5.1 seconds, all right, really small time interval. Now, you can't just use one. I mean, you have to use several. You can't just use one time interval and say, okay, hey, that's the average velocity over that time interval, so that's our instantaneous velocity. We said, no, those are not the same, right? Average rate of change and instantaneous rate of change are not necessarily and typically not the same thing. So you have to look at smaller and smaller intervals to see a pattern, right? So maybe that's the good word to use there. I want to see a pattern that develops in those velocities over those smaller and smaller time periods. So over the interval from 5 to 5.1 seconds. Now, this is nothing more than our slope formula. That's all that is. It's rate of change in our function value from 5 to 5.1 seconds over our change in time from 5 to 5.1, right? So where s, our function, is that function up above, 4.9 t squared. So when I say s of t, I'm using that function. So we're plugging 5.1 into that function, minus 5 plugged into that function, divided by 5.1 minus 5, and you get approximately 49.49. Units, 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 units. Pay attention to your units. Units will bail you out of a lot of situations where it helps you to clarify your calculations, or maybe even to check to make sure that you're doing correct calculations. When you're doing problems in physics and chemistry, where I see a lot of this stuff come in, keeping track of your units can help a lot with making sure that you're doing the actual or correct calculation. And of course, the other side of that is, if I watch the units that are used in the calculation, then I know what the units are in my final answer. So what is it that we're calculating when we say S of 5.1? Well, that's the distance, right? That's the distance that the ball has fallen after 5.1 seconds. And then what is S of 5? S of 5 is the distance the ball has fallen after 5 seconds. So that's the distance traveled between 5 and 5.1 seconds, and that's given to us in meters in our problem. And then we're dividing that by 5.1 minus 5, which is the time interval, right? 5.1 seconds minus 5 seconds. So the units up top in our fraction is meters. The units on the bottom is change in seconds, so it's meters per second. And that's a typical unit for velocity. We said it's change in position over some unit of time, right? Meters per second in this case. And so then I just redid those calculations for each of our intervals of time. So over the interval from 5 to 5.01 seconds, so I plugged in 5.01 into our function. Plugged 5 into our function, did that calculation, and again 5.01 minus 5. And I came up with 49.049 meters per second. And then over the interval from 5 to 5.001, plug 5.001 into our function, minus S of 5, divided by 0.001, and we come up with 49.0049. Now, the question inevitably has to come up, well, how close to 5 do I need to get? How far do I need to go with this? I would always recommend at least doing 3 calculations, and then you do more if you need to. So it's all about, do I recognize a pattern here in these values? So you always want to do at least 3. You do more if you need to. So if it was still not quite clear where those values were headed or what they were getting close to, then I would do closer. I would go closer to 5. All right. But with these few calculations, it's pretty obvious, I think, here that we are getting closer and closer to 49 meters per second. Now, again, this is purely an observation on our part based upon the values given in our calculations. So we're going to say that it appears that the velocity at t equals 5 seconds of our ball is 49 meters per second. Okay? But again, all 3 of those problems worked on exactly the same premise. It's the slope of the secant line and looking at the limiting values of the slope of the secant line to give you the slope of the tan line. It's just how you're coming up with that information based upon the information that's presented in your problem. Right? So have fun with that section. You're going to have to crunch some numbers a little bit. And that is section 2.1.